Welcome to Chapter 10, the 8th screencast for liquids, solids, and phase changes. For carbon dioxide, you'll notice a lot of similarity to the phase diagram for water in the general shape, but notice that there's a few differences as well, including, of course, the specific temperatures and pressures. So the gas phase, as before, is at the higher temperature, lower pressure, so it's to the right and below of this line. The liquid is in between these two phase boundary lines, and the gas is the lower temperature and higher pressure location. And we have a solid gas equilibrium line, we have a solid liquid equilibrium line, and a liquid gas equilibrium line. We've got a triple point at which solid, liquid, and gas can coexist at the particular pressure and temperature conditions, which for carbon dioxide is negative 56.4 degrees Celsius and 5.11 atmospheres. We have a critical point, and the temperature of the critical point is 31.1 degrees Celsius. The pressure of the critical point is 73.0 atmospheres, and beyond the critical temperature, we don't have gas phase or liquid phase that are separate. We just have a really either dense gas or hard to describe how exactly we were to look at the liquid, but we have the same kind of strange behavior as we did for water. And yeah, I guess that's probably enough for this one. So now let's look at example 17, where we're not given a phase diagram, but we're given some data which allows us to determine a phase diagram. So this is for bromine. It has a triple point temperature of negative 7.3 degrees Celsius, a triple point pressure of 44 millimeters of mercury, a critical temperature of 315 degrees Celsius, and a critical pressure of 102 atmospheres. The density of the liquid is less than the density of the solid, so 3.1 compared to 3.4 grams per cubic centimeter. Draw a phase diagram and label the points of interest. So we're going to graph temperature versus pressure. Just as a note, you might have seen this on previous phase diagrams. We often don't have very nice linear even division scales on phase diagrams, especially along pressure axis, because we typically go over such a big range of pressure that they look a little bit weird. So we often use a non-linear but instead a logarithmic scale. So this is not untypical at all. Here our divisions are 0.1 atmosphere, 1 atmosphere, 10 atmospheres, 100 atmospheres. So instead of going up in even addition increments, we're going up in multiples that are the same. So factor of 10, factor of 10, factor of 10. It's reasonably common also to not do that for temperature, because often the issues aren't as severe in terms of big range of temperature as they are for big range of pressure. So there is the triple point plotted. There is the critical point plotted, and the triple point and the critical point will be joined by a phase boundary between liquid and gas, that is the vapor pressure line. Now we'll have a liquid solid phase boundary, and in the case of water, the phase boundary line for between liquid and solid had a negative slope because liquid water has a higher density than solid water. But for most everything else, the solid has a higher density than the liquid, and so the phase boundary line slopes slightly positively. And notice that if we were to go from liquid to solid by increasing the pressure, we would expect that we would compress the solid and have a smaller volume for a given mass, so it would be expected to have a larger density. So that's what happens, and that's the reason for the positively sloping solid-liquid equilibrium line. We'd also expect there to be a solid-gas equilibrium line, and it has the basic same shape as the CO2 and H2O phase diagrams, but some differences, and especially differences in the specific pressure temperature points. If we get rid of the clutter of the points and their values, then gas, solid, and liquid phases as before, triple point here, critical point there. And if we made a good phase diagram, then we can answer questions like this. What phase is present at certain pressure and temperature conditions? What happens when we change the temperature or when we change the pressure, etc. So let's do these one by one. First of all, what phase is present at 25 degrees Celsius and 10 atmospheres? Well, let's just plot it. 25 degrees Celsius, 10 atmospheres, we are in the liquid phase. B, what phase is present at 150 degrees Celsius and 250 millimeters of mercury? So again, plot it, 150 degrees, 250 millimeters of mercury. Note that the pressure here is in atmospheres, so you might have to convert from millimeters of mercury to ATM to see about where to put it. And that is a gas. What phases are present at negative 7.3 degrees Celsius and 44 millimeters of mercury? That should sound familiar because those were the values given for the triple point. And at the triple point, solid, liquid, and gas can coexist, so all phases will be present. What happens when we decrease the temperature from 100 degrees Celsius to negative 7.3 degrees Celsius at a constant 50 atm? So there's 100, there's negative 7.3 degrees Celsius. We're going to be at 50 atm, and we're going to decrease the temperature at a constant 50 atm. So what happened was we went from liquid phase to gas phase, so that's called solidifying. E, what happens if the pressure is increased from 10 atmospheres to 100 atmospheres? So I think there's a slight correction from what's on your handout for the note taking. So we go from 10 atm to 100 atm, and we're going to be at a constant 300 degrees Celsius. So we're going from the gas phase to the liquid phase, and that is called condensing. And then finally we have a multi-step problem. What happens if the bromine at 300 degrees Celsius and 100 atmospheres first goes to 120 atmospheres while the temperature remains constant at 300 degrees Celsius? Then it goes to 330 degrees Celsius while the pressure stays constant at 120 atmospheres. Then it goes to, and here's a correction, 50 atmospheres while the temperature remains at 330 degrees Celsius. And then finally goes to 310 degrees Celsius while pressure remains constant at 50 atmospheres. And a couple other corrections there. So there is our starting point, and we are in the liquid phase. We increase the pressure, holding the temperature constant, then increase the pressure, holding the temperature constant. Increase the temperature, holding the pressure constant. Easy to get tangled up in this. Then hold the temperature constant and decrease the pressure, and then hold the pressure constant and decrease the temperature. And we are now in the gas phase. But notice we got to the gas phase by this sort of circuitous route of bypassing, not going over the phase boundary, because the phase boundary ends there at the critical point. So what we ended up doing was going from liquid to gas without ever boiling, which again is pretty weird, but it happens. Here is another phase diagram actually of water that shows the fact that some substances, like water, can actually make more than one type of solid phase. So water can make solid 1 or solid 2 or solid 3, etc. Many different solid phases represented by Roman numerals, and they all have H2O molecules that are arranged somewhat differently and therefore have slightly different properties. These get a little hard to interpret at times when you have multiple, let's say, solid phases, but even then, based on general knowledge, there's some things you could answer. For example, here is a phase diagram for carbon. Carbon happens to have gas phase, liquid phase, and several solid phases. And it might be tough to sort out the solid phases from each other, but you could certainly predict that the gas phase is likely to be E, because gases typically form at the highest temperatures and the lowest pressures, which is where the region E is. Now, the last thing to do is a little bit of discussion, just a summary of some types of solids and their characteristics. Ionic solids we've dealt with a lot before. They're positive and negative ions stuck together. They are brittle and hard. They have high melting points, and they're crystalline. And, for example, zinc sulfide, regular array of positive and negative ions, is an example. Molecular solids are made up of molecules that are held together by intermolecular forces. They can be soft they're typically soft with low or maybe moderate melting points, depends on the strength of the intermolecular forces. They tend to have a regular array, so they're what we call crystalline, and things like water and carbon dioxide and organic compounds make molecular solids. There are also things known as covalent network solids that are atoms held together by covalent bonds in a network. They are very hard, they have high melting points, and they're crystalline. The classic example is diamond, but quartz and tungsten carbide are also examples. And then note that carbon actually forms diamond, which is this three-dimensional array of tetrahedral carbon atoms, but it also forms graphite, which is sheets of carbon that are arranged in trigonal planar fashion, carbon atoms, and they have quite different properties, of course, diamonds versus graphite in old-fashioned pencil leads. And there's a picture of the graphite structure blown up, of the diamond structure blown up a bit. And then some things like quartz, which the macroscopic scale sort of reflects their internal geometry or structure. Metals, we've talked about before as well, are metal atoms stuck together. They're held together by metallic bonding, which is the attraction between metal ions, and metals tend to have a lot of electrons that are just free to move around, which is why they're so conductive. And metals they tend to be shiny, they can be soft or hard, usually have high melting points, and they're crystalline, and of course usual examples of metals. And then amorphous solids are when we have various things, atoms, ions, molecules, etc., that aren't in a regular pattern. They're not crystalline, and because of that, they don't have sharp melting points. They may flow. They can make curved edges when they shatter, and things like plastics are sort of the classic example of that. And the very last thing to mention is that we determine structures of solids by something called X-ray crystallography, where basically, very short form, is we shine X-rays on the crystal surface. The X-rays diffract or are sort of reflected by the atoms, molecules, or ions in the crystal, and it makes a pattern. And then the pattern can be interpreted to determine or deduce the structure of the crystal itself. And that's a fairly complicated thing to do, but the basic principle is shine X-rays, which have wavelengths on the order of spacings between atoms and ions and molecules, and you get this pattern, and the pattern can tell you something about the shape. And that is it for the official screencasts. There might be a few more posted later to answer follow-up questions.